Okay, let's take a look at section 5.5 now. I'm not going to do much out of this section. I looked at the basic constructions here, and I think you can probably make sense out of them. And especially if you look at the YouTube videos that talk about it. What I wanted to do was to do this one major theorem, 532, and then work an example from the exercises. And it won't take very long here. But we do have this major theorem here having to do with when parallel lines are cut by transversals that form congruent segments. Now, this particular theorem I've heard other places, where am I here, referred to as parallel projection. Okay. In other words, we have three parallel lines here. These two sides are the same length, and when you project those things in a parallel fashion here, then the other sides are going to be the same length. Okay, this really has two cases to it. We have that either L is parallel to M, the transversals are parallel, or L is not parallel to M. Okay, and we'll break it down and work these two cases. Like the book, I may leave out some details. I think I'll be a little more detailed than they are, but it's if you write down every single little detail in a two-column proof, this can be a bit long. So we're going to look here. Here's our proof with case 1. L and M are parallel. Okay, this is pretty easy. Okay, because and again, I'm not going to do a two-column proof. I'm just going to talk my way through this. L and M are parallel. This means that ABED is a parallelogram. And that also means one of the things about a parallelogram is that opposite sides are congruent. So this means, among other things, that AB is equal to DE. Okay, L is parallel to M. This means that down here at the bottom, that BCFE is a parallelogram. And that means that BC and EF are congruent. So BC is equal to EF. Now, going back up to the top thing, we were given that AB equals BC. So since AB equals BC, we can string a lot of these together. DE is equal to AB, which is equal to BC, which is equal to EF. So these two things are equal, which is actually a application of, I guess, a transitive property a couple of times. Okay, that's the easy one. When they're parallel, that's easy. When they're not parallel, it's a bit longer here. L and M are not parallelogram, are not parallel. So I can't appeal to parallelogram having equal opposite sides. But I'm going to make a parallelogram. I'm going to use the parallel postulate. Okay, extend the page here. Parallel postulate I can find a line through D that's parallel to L. Lines through D and E parallel to L exist. Okay. So what I'm going to do then is I'm going to draw such a line through D that's parallel to L. Oops. And I'm not really concerned with the whole line. I just want to know, just want the part that goes down to line BE. And I want the line that's parallel through to L that goes through E as well. And again, I'm not going to draw the whole line. I'm just going to go to where it intersects with CF. So let's let X, let's call this point X here, be, excuse me, let's say let X and Y, let's call this point Y, where be the points where these lines intersect BE and CF respectively. Okay. So in the process, what I've done is I've formed some little triangles over here. We have triangle DXE and triangle EYF. What I'm going to do is to show that those two triangles are congruent. Okay. So the first thing to do, show in that, is that by having these parallel line segments, the DX segment and the EY segment, I've formed parallelograms up here, ABXD and BCYE. Okay, so ABXD is parallelogram. So AB, okay, this is supposed to be a so, then you can't read that. So, okay, side AB is congruent to its opposite side, DX. BCYE is also a parallelogram. So BC is congruent to its opposite side, EY. Okay, so the two little red sides here are congruent. Let's see, what else can we say here? Let's do this much. Let's look at an angle here. Let's take a little green thing here. Okay, I'm concerned about this this angle and this angle. Okay. Right. So let's talk about them. Right. Angle ABE. Okay, so this green one here is congruent to angle DXE. Okay, because these are parallel lines cut by a transversal, they're corresponding angles. Okay, and for the same reason, okay, this angle at C, BCF, and EYF are congruent. BCF and EYF. Okay, and for the same reason, okay, I have two parallel lines here, lines BE and CF cut by transversal L. That means angle ABE is congruent to angle BCF. stringing together a bunch of congruences, transitive property, hence angle DXE is congruent to angle EYF. Okay. Now, one more set of angles I'm going to work with, and these are a little bit easier to see perhaps. Let's use red to point them out. Are these angles up here? Okay. I didn't say this, but DX is parallel to EY, since both are parallel to L and we're in a plane, comma. So angle EDX is congruent to angle FEY because they're corresponding angles. Formed when two parallel lines, DX and EY, are cut by transversal M. I think we have it all here now. I have the two angles at X and Y are congruent. The two angles at D and E are congruent, and the line segments joining them are congruent. So hence, triangle DXE is congruent to triangle EYF. By angle, side angle. Okay, and finally we can do it. Okay, we're just about done here, and that means that DE is the same length as EF because they're corresponding parts. Okay, so that's a fairly detailed little proof, much longer than what they have there. I hope you can follow it because I know you can't read it, but I wanted to do that. This is an important theorem here. As I said, it's parallel projection. We'll use this at other times. And there are some other versions of this as well that have to do with proportions when you project them, but we'll just kind of go with this for now. It turns out to be an important theorem. Okay, I wanted to do now one example from the book. This is number 13 on page something or other, page 285. Construct a rhombus given the length of a diagonal and the angle between that diagonal and the side of the rhombus. Well, first thing, if you look in the book and look at my picture, I have drawn a different angle. It's kind of strange when I was working this problem. It worked out a little too neatly, and because the angle that they have in their problem number 13 is virtually a 45-degree angle. And whenever you put up problems like this, you really shouldn't choose special angles like 45 or 60 or 90 or something. You should pick something odd. Anyway, I wanted to redraw the angle because theirs was just too nice. What I've done over here in the right-hand frame is I have recopied the excuse me, the line segment A, the same length, and the angle P. And let's make this sort of assumption here. Let's put the diagonal on the slanted line, and let's put the side of the rhombus on the horizontal line. Okay. It doesn't matter which one we pick, but I'll pick to do this way. Excuse me. Okay, well, first thing I'm going to do is transfer the length of the diagonal, the A, here to the slanted side that I chose. So let's pick us a compass. Now, if you've never tried to use the compass tool on a smartboard, let's just say it's an adventure. Okay. It's one thing to do it on an actual smartboard in front of class, but to do it here using a mouse and the computer screen is it's a chore. So my drawing here is not going to turn out to be nearly as accurate as yours should be when you use your own ruler and compass here. So first thing is to translate this distance down here. So I set my compass to measure that length. And that's pretty close. Okay, put the pointy end, come on, the pointy end on the vertex, and this distance is my diagonal. Okay, now, what do you know about, let me go back. Okay, I tell you what, let me just start all over again here, because I don't think I had my pointy end on the vertex. And the distance from P to wherever this mark is, that's going to be the diagonal A. Now, what do you know about the diagonals of rhombuses? There's a whole bunch of things about them there. One of the things is that they are perpendicular bisectors of each other. Because they are diagonals of a parallelogram, they bisect each other. Okay. Because the sides are the same length, you can show that they're actually perpendicular. So what I'm going to do is to just go ahead and draw and figure out where the perpendicular bisectors are. Okay. So my diagonal is going to go from P to here. Okay. And now to get the perpendicular bisector, okay, I mark off the other half circle there, and the perpendicular bisector will be somewhere on, whoa, I need to change that on that line. Sorry about that. Let's make that right skinny. Okay, tell you what, let's make that red also. Our diagonals are going to be red. So the diagonal is going to be on there somewhere, and I'll put it in dashed because that's not my diagonal yet. Actually, I can see it now. You may not be able to see it, but I do. So let's see. Tell you what, let's go ahead and put in A. Here's A. Oops, it's supposed to be a straight line. Now you can see where I've missed some things here. That's what happens when you try to draw this on a, why does that do that? When you try to draw this on a smartboard program. But that's a diagonal A, and the other diagonal is going to be on this dashed line somewhere. Okay, now what's going on here? This needs to be black. Okay. What else do you know about diagonals and rhombuses? Well, the diagonal of a rhombus bisects the angle where it of the rhombus. So in other words, if the side of the rhombus is down here on the black dashed line, then the other side of the rhombus here is going to be, well, that's just half of the angle here. So in other words, if I, whoops, figure that distance out and go over here and measure that same arc, okay, then from here to there, and I don't know why it still does this. Make this dashed and black. Okay. Okay. Then the other side of the rhombus is along this dashed line. Actually, I think we've got it now, right? Because let's go ahead and just draw the rhombus in. And here's where I do want it to be fat and green. Go from P to there, to that diagonal. Then we go from here to the other diagonal, okay, to this point here where that other side will intersect the diagonal, then back to P. Okay. That, my friends, is a rhombus with a given diagonal and a given angle that the diagonal makes with one side. Okay, make sure you understand this because there's a problem on the test that where you have to do a construction something like this. And that's all I have from this section. I think it's a pretty straightforward section.